Can all of you see me, or am I too short to stand behind the podium? Well, I guess I can't help it, but I can help you get better network performance by using worse quality of service using RC3, which is what we're going to talk about today. So we'll start this talk with discussing what are the issues with current congestion control and why we need something like RC3. This will be followed by understanding the scope of our performance gains using a very simple theoretical model, and then some of our design details, our NSU simulation results, our Linux implementation and evaluation, and finally some of RC3's challenges and future. So Van Jacobson did his classical work on congestion control in 1988, and after that there has been plenty of work on congestion control, and most of us think it's a solved problem. So why am I standing here still talking about congestion control? Well, we see that avoiding congestion collapse is not the only goal of congestion control, and flow completion time really matters. In fact, it by and large defines user satisfaction. And there has been plenty of work within data centers and some outside and wide area networks that try to shave off even as little as 10% of the total flow completion time. With RC3, we provide a somewhat different take on this problem, attacking its root cause with a simple yet effective solution. So in a nutshell, our design is very simple. We aggressively send a large burst of additional packets from the flow using low priority, or what we say worse quality of service, filling up only the spare capacity in the network. And this helps us in reducing the flow completion time while ensuring that we don't harm the regular high priority traffic. And it also allows us to better use the network resources. So why does this simple scheme work? Let's understand that with an example that represents the current scenario. Supposing I have a sender, Van Jacobson, who wants to send some data to Windsurf through the network provider, David Clark. Now, both the sender and the network provider would like to account for high congestion, but in different manners. The network provider would like to accommodate a large burst of traffic during peak hours, or may want to keep sufficient headroom in case some link failure occurs. And so he decides to over-provision. And we see that the average link utilization in the internet is only between 30 to 50%. The sender, on the other hand, works on the assumption that the network might be highly congested, and so he decides to ramp up slowly. And this is what happens in TCP. We start with a small initial congestion window, growing it exponentially with every RTT until we hit congestion avoidance. Now, while we're in the congestion avoidance mode, assuming appropriately sized buffers, we are able to fully utilize all of the available capacity in the network. But we end up wasting a large amount of capacity during slow start, resulting in long flow completion time. So what is the root cause of this wasted capacity and long flow completion time? We see that any congestion control mechanism has two goals. The primary one is to fill the pipes in the network to achieve high throughput, and the second goal is to do no harm to the other flows that are sharing the network while we are trying to fill the pipe. And these two goals conflict with each other, the first one requiring us to be more aggressive, and the second one requiring us to be more cautious. And the traditional approaches so far try to achieve these two conflicting goals through the single mechanism of finding the sending rate. We see that TCP ramps up because it would eventually like to fill the pipe and achieve high throughput, but it does so cautiously using slow start because we don't want to harm the other flows. So with RC3, we resolve this conflict with a very simple idea. We can just decouple these two goals by using priorities. We can fill the pipes with low priority additional traffic to get high throughput, and since we are doing this at a lower priority, we do no harm to the regular high priority traffic. So we already saw how TCP is able to completely fill the pipe during congestion avoidance, but there's a large amount of empty space in the pipe during slow start. So with RC3, we fill this empty space in the pipe with additional low priority packets, while we have regular TCP ramping up at higher priority. And we see that as this high priority traffic ramps up, the low priority additional traffic gets naturally throttled until the high priority traffic reaches congestion avoidance mode. Also, now that we are able to achieve very high throughput right from the first RTT, the flow completes sooner. So, coming back to our example, supposing Van wants to send a short 7-packet flow to Wind, then with TCP under slow start, he would start with 1 packet, get an ACK for that, then he would send 2 more packets, get ACKs for those, and then finally, he would send the remaining 4 packets, and we see that this short 7-packet flow would take him 3 RTTs to complete, even though there was enough spare capacity in the network to send all 7 packets in one go. Now with RC3, he can send his first packet at the highest priority, followed by remaining 6 packets at a lower priority, and the flow would therefore complete in a single RTT. So this simple example must have given you some basic idea about how RC3 helps in reducing the flow completion time. And we can understand the trends in our performance gains better by using a simple theoretical model. So in our model, we plot the percentage reduction in flow completion time as a function of flow size, and it depends on the initial congestion window and the available delay bandwidth product. We see that if the flow size is less than the initial congestion window, both TCP and RC3 would complete in a single RTT, and we would expect to see no gains. But beyond that, if the flow size is less than the initial congestion, more than the initial congestion window and less than the delay bandwidth product, then the number of RTTs taken by TCP would increase with increasing flow size, whereas RC3 would still finish off in a single RTT, and the performance gains will increase logarithmically. Beyond that, the transmission time dominates, which is the same for both TCP and RC3, and the performance gains are likely to decrease with flow size. It's also clear that as we increase the delay bandwidth product, our average performance gains would increase, showing that something like RC3 is more suitable for wide area networks where we have large RTTs. So with that, let us understand some of our design details and how we achieve these gains. Now, before moving into the RC3 design at the end host, let us look at how we implement the worst quality of service. That can be done by simply using the priority queues already present in the routers, and the priorities can be carried by the packets, possibly in the DSCP field, with the default priority being 0, and lower priorities represented by higher numbers like 1, 2, 3, and so on. Now, at the end host, the RC3 design is very simple. We just have two parallel control loops. The first one is a TCP control loop that is mostly unmodified, and it sends packets at the highest priority based on the TCP's congestion window, which grows normally. And then we have this extra recursive low priority, or the RLP control loop, that sends additional packet at a lower priority. Now, what exactly are these low priority packets that we send in our RLP control loop? Now, note that our main aim here is to reduce the flow completion time, and that would happen if there's minimum overlap between the packets sent by the TCP control loop and the RLP control loop. So to ensure this, we send the low priority packets from the very end of the buffer in a backwards direction. So at the receiver, we basically have two streams of traffic. The first stream comprising of the TCP packets sent from the very beginning of the buffer in a forward direction, and then the second stream comprising of the low priority packets sent from the end of the buffer in a backwards direction. And when these two streams moving in the opposite directions converge at the receiver, the flow completes sooner. Now, let's come back to our example. Supposing WAN wants to send a long flow to Wind. He would send his first packet as per TCP's congestion window at priority 0, and he can fill up the remaining capacity in the network with lower priority 1 packets from the end of his buffer. Now, so far, so good. But what if Sally hears about RC3 and wants to use that to send a short flow to Wind, comprising of 1 high priority TCP packet and 2 more low priority packets? So let's see what would happen at the queue in the bottleneck. Say WAN's traffic arrives first and fills up all of the buffer space in the queue. Now when Sally's traffic arrives, her priority 0 packets will be able to preempt WAN's priority 1 packets, but her priority 1 packets would simply get dropped because WAN's traffic was hogging all of the buffer space. And this is very unfair to Sally, who now gets no benefits from RC3. So how do we ensure that both WAN and Sally can use the spare resources in a fair manner so that both of them can get good benefits from RC3? So for that, we use the notion of low priorities recursively. We have multiple priority levels, and we send exponentially larger number of packets at each priority level. So we send the last X packets at, say, priority 1, the next 10X packets at priority 2, the next 100X packets at priority 3, and so on. And this ensures that a flow of one size can now only compete with other flows of comparable size, and we therefore get maximum fairness. So to quickly recap RC3 design, we have two parallel control loops at the end host. The first one is the unmodified regular TCP loop, and then we have this additional recursive low priority loop that sends extra packet from the end of the buffer in a backwards direction at lower priority, and we use multiple priority levels to achieve maximum fairness. Now we implemented this design in NS3, and let us see how well it performs in practice. So our simulation was done on internet to network topology with 1 Gbps bottleneck bandwidth and the standard workload used in wide area networks, and you can look at the details in the paper. So how does our simulation result compare with the simple model we looked at before? So just like our model, we plot the percentage reduction in flow completion time as a function of flow size, and we see that our simulation results show similar trends as predicted by our model. And we see a few interesting things here. First one is that although model doesn't predict any performance gains for these very short flows, our simulation results show that even these short flows are benefited. This is because the longer flows can now complete sooner using lower priority service, which reduces the congestion amongst the highest priority packets, benefiting even these short flows. Also, for the longer flows, our simulation results show slightly smaller gains than our model. This is because the model is very simple and does not account for queuing delays and drops, which we see in our simulation. On an aggregate, we see that we get a 44% reduction when averaging across flows and a 74% reduction in flow completion time when averaging across bytes. So how does RC3 compare against other schemes that have been proposed to reduce the flow completion time? We'll look at two of these schemes in our talk. There are more in the paper. So there have been proposals to increase the initial congestion window to 10, which is already implemented in Linux, and to even as high as 40 or 50. Now suppose I increase my initial congestion window from some value I to say some value I dash. Then we see that unless I dash is as high as the delay bandwidth product, the performance gains that we would see is less than what we would get with RC3. Also, simply increasing the initial congestion window, making the flow more aggressive, has the fear of harming the shorter flows in the system. And we validated that through our simulation. We increased the initial congestion window to 10 and to 50, and we compared the results with RC3. And as expected, the shorter flows were penalized when we simply increased the initial congestion window, and the longer flows gave stronger gains with RC3. We next compared RC3 with a scheme based on explicit rate negotiation called rate control protocol, where the routers compute the fair share of every flow, and that is sent back to the sender using during the TCP handshake. And we see that, again, the short flows were penalized with RCP because of more aggressive behavior by long flows, and the longer flows give similar gains with both RCP and RC3. Then we tested RC3 on a number of different scenarios, and we have more comparison results, and you can look at the details in the paper or come and talk to me after the presentation. We next implemented RC3 in the Linux kernel, so let's see how that went and what were our results. So our Linux implementation was fairly lightweight. We just required about 100 extra lines of code to implement the RLP control loop to send the low priority packets and to handle the receipt of the low priority data packets and the ACKs. And the best part about our implementation was that we only touched the base TCP files. We didn't have to touch the files specific to different congestion control algorithms like Tahoe, Reno, Big, Cubic, etc., which means that we can easily enable any of these congestion control schemes or anything new that comes up, and all of that would be compatible with RC3. And we see that RC3 had the shorter flow completion time as compared to regular TCP, and we had similar performance trends that we see in the simulation and in our model. But if we compare the flow completion time in a simulation to that in the Linux implementation, we see that RC3 had a higher flow completion time in the Linux implementation, especially for the long flows. This is because the low priority packets at the receiver arrive out of order and are processed by the slow path in the networking stack, resulting in high per packet CPU overhead. Now note that this does not make us perform worse than TCP. We always perform better than TCP, but we still try to mitigate this problem as follows. Now, in order to reduce the processing overhead, modern Linux already supports schemes like TSO and LRO, where multiple segments can be processed by the networking stack as a single chunk. Now we make sure that RC3 is compatible with these enhancements. Whenever TSO is enabled at the sender, RC3 would treat the multiple segments chunk as a single packet when assigning the priorities and sending it out on the wire. And this ensures that the receiver receives this chunk as a short in-order bursts of packet where it can be aggregated by the NIC and sent up again as a single chunk to the networking stack. And we see that when both TSO and LRO is enabled, the per packet processing overhead can be reduced by almost 50%. Now, some of you might be wondering whether RC3 will perform nicely in all cases, or whether we can just go and deploy RC3 tomorrow. Well, that may not always be the case, and we'll briefly discuss some of these concerns. Now, there are some cases where RC3 will have smaller benefits. The first two are obvious. If we fill all of our available capacity with high priority packets and we don't have enough spare capacity to send low priority packets, we would expect to see smaller gains with RC3. Also, if the queue in the bottleneck is not big enough to hold all of the low priority packets, some of them may get dropped, again reducing our performance gains. And if the application itself is sending smaller chunks of data to the networking stack, RC3 can't make full use of the available capacity, and again our performance gains would decrease slightly. But again, in all of these cases, we never do worse than TCP. We are as good as TCP, if not better. Now, there are also some deployment concerns that we are yet to fully deal with. So the first one is that of partial deployment. Supposing there are some ISPs that support low priority service and there are some that do not. Then when a flow encounters a router that does not support low priority service, we have two options. We can either drop all of the low priority packets, falling back to regular TCP and not getting any gains from RC3, or we can allow all of the low priority packets to go through at the default priority, therefore competing with the highest priority traffic. And in the second case, some of the short flows might get penalized. Another concern that we have is that of middle boxes. Now, as per some recent studies, there may be a bit of a hurdle in deployment of new TCP schemes, and it is still unclear as to how middle boxes would affect RC3, which simply results in reordering of some packets. Wireless is another area that we need to think a bit more about. Now, in a wired network, it is easy to ensure that a low priority transmission will never interfere with a high priority transmission. But in wireless, where we have issues like interference and collisions, such clear demarcation of low and high priority traffic may be a little difficult, and that is part of a future work. But coming to future of RC3, we see that our performance gains are likely to increase with time since they increase with the delay bandwidth product. RC3 may not be a very good fit for data centers today where we have short delay bandwidth products, but if we look at a futuristic data center with a bandwidth of 100 Gbps, then in that case, RC3 would give us 45% reduction on an average. So to summarize, we have a very simple design where we send additional packets from the flow using several layers of low priority service. And since we're using only the spare capacity in the network, we do not harm the regular high priority traffic. And this simple scheme gives us 40 to 80% reduction in flow completion time. So thank you. For those who are interested, our simulation code is there on GitHub. And I'm happy to take questions now.
Nice idea. Dong Soo Han from KAIST. Is there any mechanism that ensures fairness amongst the low priority traffic?
So that is what we do by our recursion, a multiple priority level scheme.
I see. So you need to have multiple priority schemes in order to ensure fairness.
Yeah.
Okay.
That ensures fairness amongst low priority.
How many is this sensitive to the number of priority queues?
No, so we have this exponential spacing of packets across priority levels to ensure that we can accommodate a large flow within feasible number of priority bits. For example, like 8 priority levels can accommodate up to a terabyte of a flow using the exponential scheme. So.
Thank you.
So I have a question for you. So it seems like you're increasing the sender buffer size.
Yeah.
Would that have some effects on performance, like delay and so on and so forth?
So I don't think that would have any effect on the delay, like increasing.
Any other effects on performance, or?
It's not really a performance effect, it's just that the socket would consume more memory, but I think like cheap memory is now becoming increasingly available in future, so that doesn't look like a major concern.
Question Raichu, Polting Bucharest. So yeah, I think this is really cool. I was trying to sort of go through drawbacks in my mind while you're presenting it. So TCP is sort of very sensitive to like the ACK lock and stuff. So you're sending more packets, and then you probably drop most of those in cases where you have congestion. So I'm wondering, what's the effect of that? Because you may be dropping like half a window or something. So you're really reliant on like SAC working spot on. And yeah, I mean, did you see any problems with that? I mean, is it working in this regime? Because this is not what TCP was meant for. Like you're supposed to lose one or few packets per window, not half of it or most of it.
So the thing here is we have this clear demarcation of the TCP traffic and the low priority traffic. The TCP traffic is at a strictly higher priority, and we start from the first packet in the buffer going in a forward direction. And all of this extra traffic that we are sending is from the end of the buffer, which does not really interfere with the TCP traffic. And also the receiver sends all of the ACKs for the low priority traffic at a lower priority. So in our sender, we can demarcate between the high priority ACKs and the low priority ACKs. And that won't interfere with the TCP logic.
But there's a single cumulative ACK, right? I mean, you don't have like different ACKs for the different things, right? It's like still a single TCP connection with a single cumulative ACK and different SAC blocks.
Oh, so the cumulative ACK will proceed as per the TCP logic, because TCP is the one that is sending from the beginning of the buffer as we go forward. And then when the low priority traffic sort of overlaps with my TCP traffic, only at that point will my cumulative ACK become higher than what I've already sent out. And that is sort of like a good news for us that, okay, our RC3 packets have gone there and they have helped us. And then we can kind of do some tweaks in our sender buffer saying that, okay, now I have actually sent at a lower priority and I can advance my sequence number to a higher cumulative ACK.
Yeah, I want to follow up, but
Yeah, we have the details in the paper, or you can come and talk to me offline.
Hey Radhika, excellent talk.
Thank
So
you.
what kind of switch buffering model are you assuming? Do you assume that you can drop lower priority packets once they're admitted?
Right, so that is the model that we are assuming in our simulations, that we drop based on priority and we schedule based on
Do you
priority.
think that's realistic?
So in reality, it may not always be there. What we can do is we can have like the buffer allocated for the highest priority traffic as it is, and we can add additional buffer for the low priority traffic, and that would give us similar gains as well.
Okay, thanks.
Thank you.
Hi, Miguel from DynamoDB. Always great to see work on the congestion control in the startup on TCP. It's a big problem for many of us. My question is very similar. Like in real world, you will have many bufferings happening on many devices and endpoints or middle boxes that will not allow for QoS. So real world experiments, are you going to follow up on that? And when to see this on mainline kernel?
Yeah, so we are planning to follow up on some more real world experiments, and hopefully we'll figure out all of these issues and try to come up with ways to work around them. So that's a part of our future work. Thank you.
Yeah, good talk. Thanks.
Thank you.
I'm Nadir from University of British Columbia. My question is about the last part, deployability part.
Right.
Like you said, there are two types. Some of the routers can be do not support the priorities, and you claimed that even if it does not support the priority, it's not a problem. I think if it does not support, then your both priorities are being treated equally, and all of them will get dropped.
Yeah, so I never said it's not a problem. It's not that big of a problem. We can always fall back to regular TCP. We won't do any worse. But yeah, we are not getting any benefits from RC3 in that case. And then we also have this result showing that if some of them don't support priorities, then what will happen? Let me just... Yeah. So here we see that if like, say 20% of the routers don't support priorities, then we still get good benefits. But if say 50% of the routers in the network don't support priorities and we send all of the traffic at the default priority, then these short flows can get penalized. So it depends on what we want to do, whether we would like to drop all of the low priority packets falling back to regular TCP, or whether we should allow all these short flows to be penalized at the cost of improving the flow completion time of the longer flows. So it is still a debate as to what we should do in that case.
Okay, thanks.
Thank you.
Excellent. So let's thank the speaker.